Start recording and share our PowerPoint. So today we will do one more thing. We start our assembler. Oh, our assembler. Where is my? Okay, so assembler. So now where are we? So we have finished our physical layer, and let me see, can I do this please? Okay. So we have we finish our chips and logical gates. We learned NOT, AND, and OR gates. These three basic gates. Of course, when you do the implementation, so this one we will use the NOT AND gate. So we have NOT AND gate. Okay, so we finish our logical, and we can do comparison. And get the truth value, right? We can do the truth value. So any logical expressions, we can use the logical gates to finish this logical stuff. And then we move to, we do the arithmetic logic. So you can use the logical gates to achieve the arithmetic. You can do addition, you can do minus, you can do multiplication and division. But in our hack machine, actually our hack machine, we only deal with addition. So minus you can do two's complement. So this one is quite easy. But for the multiplication, we need a high level. So we need a software to help us. So multiplication and division, we use a high level. So for the hack machine, so our special machine, we only do addition. And then the last portion is for the sequential logic. So sequential logic, we have already done the counter as well as the memory, right? We build the memory. We have register, DFF, then register, then we have the main memory. Okay, this is the logical gates. We finish our computer architecture. So computer architecture, we do the hardware platform. So you know how CPU process the things. The CPU will do actually two logical circle. One is the execution. So when you give the expression, it will do the execution. And another thing is called the fetching, right? So we do the fetching part. So for the fetch circle, is actually determining which line of code will be the next. So the easiest one is you just move your pointer, the PC pointer, program counter increase by 1. But sometimes you will jump to other places, so you have the jump parts. So you have JLT, JLE, so JGE, something like that. So you have you have 7 different jumps, and this one is for CPU. And the hardware platform also need to do one more thing, is CPU plus main memory, right? We have the MEM. So memory. So for the memory, you build from the logical gate, but this memory you need to assign address. So address is the most important thing in the memory. So in the memory, we have 2 parts of memory. Just to briefly review. One is RAM. RAM is used to store your code, right? So RAM is 32K, right? 32K RAM. And the other part is the RAM, right? RAM is a little bit complicated. We have 3 parts for the RAM. One part is data, one part is for the screen and one part for the keyboard. Still remember? So this one, make sure. Then we learn the machine language, right? So the machine language is tell the CPU how to do the execution and jump to fetch the next code. And also it will give you the memory address or the data register. So as together with CPU, you will do is plus a certain register. We have D register and A register associated with CPU. Okay, so far so good. Okay, now today we will move to this portion. We have the assembly language. This assembly language, we have already learned some assembly language. Now this time we will do is assembler. Assembler, the major things is for the assembler is do one thing is, okay, this is assembly language. For example, in the A language, I have at 16, for example. Then at 16, this one, machine language doesn't know what do you mean at 16, right? This is assembler language, a symbolic language. Then assembler will do this translation to say, okay, this is, I will translate to 16-bit, right? 0, 0, 0, 0, 4, 0, 6, 0, 7, 8, 9, 10. I have this one is 0, 1, 2, 4, 8, 16, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. All right, so this is directly translation, right? So assembler will do this work automatically. So why we care about assemblers? So assembler actually is a little bit complicated program tricks, but it's not that hard. It's directly, it's like a translator. This translation is between one language to another language is a one-to-one translation. Okay, so this is looks like assembler work. One-to-one, this one is a symbolic, this one is symbolic, and this one is a binary, right? So we have binary representation, so this is one-by-one translation. Assembler will do certain things, but assembler will also have certain kind of actual work need to do. For example, if I say, I don't give you at 16, but I give you, say that, okay, at I, this is a variable, then assembler need to do some more work to accommodate variables. Okay, so for now, we ignore the details, but just to give you the whole picture. So this is the source code, assembler source code. And I have at I am equal to 1, let I equal to 1, and at summation, I want a sum equal to 0. Then I will do, if I greater than rum 0, then I will do the whole work. Of course, this one is after your assembler, then it will give you the target code. Okay, this is the fundamental idea. And then this machine code can be executed by our CPU or by our hack machine. Program challenge is extract the program's semantics from the source program using the syntax rules of the source language. So this one is actually, how do we do this one? So we have A instruction and the C instruction, right? So we can do that. Re-express the program semantics in the target language. using the syntax rules of the target language. Okay, so target language looks like this is the A instruction, and look like this guy is the C instruction. Right, so this one is just a one-to-one translation, so it will be very simple. Okay, and we need to do two parts. One is, okay, this is the real instruction. For example, m equal to 1, this is real instruction, right? And or d JGT, so this one is the real instruction. Another thing we need to handle is symbol. For example, at I, at a summation. So like this one, I need to have a way to translate I and the summation to a certain number. And of course, another thing is like a loop or at right. So it looks like this. For those guys, I need to have ways to translate those symbols to numbers. Okay, so this one I will skip for a while, then we will look at how we do the symbolic translation assembler. So the first easy part is A instruction. So for A instruction, for example, I have at 16 is just the last time we do 8 at 16. So if it's A instruction at 16 is quite easy, right? Our leading bit will be 0 because it's A instruction, and then 16 will convert to the binary. 1, 2, this is 1, 2, 4, 8, 16, right? Then you put it into 16 bits. Okay, so I will not write too much, so I will do this one. Totally 16 bits. So this one is for A instruction. Right? So this is quite easy. Then the next one is C instruction. C instruction is also quite simple because we have the ways to do that. Okay, I will. Oh, C instruction is looks like this. So C instruction, okay, so this is A instruction. C instruction is quite simple. Hey, so this is a C instruction look like we have already learned before the midterm. So this is instruction table. So A and C1 to C6, how we do this, and this is the code. And then I will say, okay, this is the destination I want to put, and here is the jump, right? So for example, I want D. Translation is quite simple. How do we do that? Is okay. I want to do D equals to D plus A and jump. So J G T. Okay, greater than. So now the assembler will do an easy job is just to look at what is your computation, right? Since this is the C instruction, so it will do 111. So to tell the system this is the C instruction. And then I want to do the computation is D plus A. So D plus A is here. So D plus A is here. So it will be 0, D plus A. So 0, 0, 0, 0, 1, 0, right? 0, 0, 0, 0, 1, 0. Right, so this is A and C1 to C6. Then the destination is D. So destination is D. So D register is 0, 1, 0, 0, 1, 0. And the JGT JGT is here, so jump when greater than, so this one will be 0, 0, 1. Right, so now doing this, it will translate. This one you have already done in the midterm, right? You do line by line translation. So our assembler will do the same thing. Our assembler will do the same thing to say, okay, when I see this one, I will first separate this line of code to 3 parts. One is computation, one is destination, and one is my jump. Okay, first separate into 3, and then I will fill in. If I look at this one, I have a table in my assembler. So if I see D plus A, I look at this to compare each one. If it's the same, then I will use this one and fill in C1 to C6 as well as A here. And then I look at the second part is my destination. Okay, this time is D, so I will look at this table and find the 0, 1, 0 here and fill in. And the last portion is JGT, so when I see this one, it will be there. So it's quite straightforward. Okay, so we finish A instruction and the C instruction. Now, the third part is the symbol declaration. So symbol declaration is here. In this example, I have symbol I have symbol summation, I have symbol right. So I have symbol right and the symbol loop, right, and the symbol end. Okay, this is symbol. You can see this is actually, we can separate into 2 parts, 2 types of symbol. One type is looks like I and the summation, I and the summation. This one is a variable, right? This is a variable. So this is a variable. And another one is used as a control, right? This one is a control, CTR. So control. So you have a loop, you will have a loop, so you have somewhere to jump to here. So this is the control part. And the right is also the control. So this is also control, and the end is the control. So our symbol declaration, actually, we have 2 types of symbol, and we will learn it later. And the last one is a comment or white space. Comment looks like this guy, or looks like this. So if this one go to right, so this one is the comment. Just like your high-level language, comment to assembler means nothing, right? So you don't do anything, but since it's a same comment. And there's a white space. So we have certain kind of, if you write certain white space between symbols, then this one is actually when you do assembler, need to trim it. You have to trim it because the white space is nothing. So the challenge thing is translate the program into a sequence of 16-bit instructions that can be executed by the target hardware platform. So this translation is for A instruction, we have already done. It's quite easy. Just look at the value. But the A instruction has 2 parts. Previously, if I just give you the non-negative decimal number, it's quite simple. You just convert to the binary representation. If value is a symbol, we will do it later. So in C instruction is also quite easy because there's no symbol anymore, right? So this one is you just look at table lookup. So this one is quite easy. So this one is translation is simple. Okay, so now we go to our assembly logic. So for each real command, parse the command, break it into its underlying fields, especially for C instruction. C instruction, you should do compute, you have the destination, and you may also have the jump part. So this, you should break it into underlying fields, especially for C instruction. Also, sometimes you need break into parts for the A instruction. For example, I have a variable associate. And the beginning one is at. So this one is kind of the leading character. Special character tells me that this one is the A instruction. So I break into the fields, and for A instruction, it just have two fields. One is from the at. This one is the special character tells me this is A instruction. And the next one is the value or the symbol. Okay, now A instruction, if it's A instruction, it will replace the symbolic reference with the corresponding memory address, which is a number. So this is the number. We will do it later. For C instruction, for each field in the instruction, generate the corresponding binary code. Okay, this is just a little bit summary. Assemble the translated binary code into a complete 16-bit machine instruction, and write the 16-bit instruction to the output file. So this is whole thing for the assembly. If you build assembly code, this is the whole thing. Is you, each command you will read and separate, and based on the instruction, you do the translation, and then you write to the output files. I think two groups will do assembly, right? So assembler. So if you do assembler, you also need to follow this style. But your assembler is a little bit simple. Still, you need to do this kind of thing and generate the machine code as output file. Hey, so far so good? Okay, then we move to the next part, is how we solve the symbol resolution. So how do we replace the symbol? Okay, just a quick test. So to make sure, oh, okay, anyone can tell me? Okay, anyone can give me the answer? If you don't know, please check back to the last slides for the computer architecture and find the answer through the slides. Okay, so this is the slides showing the answer. So this is the range for the data memory. So it's from 0 to 16,383. Oh, this is for data. So let me write. So this is from here to here. So this is for data memory chip. And for the screen, it's from 16,384 to 24,575. And for the keyboard, it's just one address, 24,576. Okay, so this is the address range. So assembler should first know where is the memory address range so that it can know. If you give me the assembly to say that, okay, at I, it probably is referred to the memory, but if you say at screen, you probably will start at 16,384. So then the assembler knows that where to translate. So far, so good? Okay, so I will shut down this one. And then we will move back to our assembler. So, okay, so now we deal with our symbols. Oh, let me see what time. Okay, we still have 10 more minutes. So, okay, so for this one is a typical symbolic hack assembly code looks like. So we have, so this time you can translate for screen. Assembly typically have many symbols. So the labels that mark destination of go-to commands. So you have, for example, my symbol is R0 and counter, screen, loop, X, right? Counter, something like that. So this one is too many symbols, but this labels sometimes is mark special memory allocation, for example, screen. This is very special memory allocation. This one is only go to the screen part. So you add screen means you try to get the info, write to the information or get to the information from the screen. So I have the variables So like X here, like a counter here, this is the variable. And falls into all these symbols has falls into two parts. One is the user defined symbols. For example, X counter. So X and counter, this you create by user. And another one is predefined symbols. This is predefined like the screen, right? This screen is predefined symbols. And another one I will introduce is R0 is predefined symbols. And for those symbols, and we have the label symbols, and another one is the variable symbols. So the label symbols, for example, the loop. So we use it into the control, right? This one is used for the control symbol, or we call it the label symbol. This usually is the uppercase in the hack machine. And the variable symbols is looks like X and counter. This one is the variable symbol. This one may refer to certain kind of things is in the memory. So our variable symbol, usually for our memory, we start from 16. So why is 16? Later I will discuss, because we have already reserved the previous 0 to 15 as a special use. So now the question is, who does all these things? Automatically assignment. So question, who does all the automatic assignments of symbols to RAM address? Anyone can answer? Yeah, CPU usually is our assembler, right? Not a CPU, right? So this one is the part of the program translation process. So the assembler will do that, not CPU. CPU cannot do this assignment. CPU can only do the calculation, right? Computation, not do this assignment. So assembler will do that. Okay, now we look at our predefined symbols. The assignment for assembler. So the first one is R0 to R15 are automatically predefined to refer to memory address from 0 to 15. This one is already occupied. And we have another occupied predefined symbols like screen and the keyboard. So screen for the screen access. So this one is address range from 16,384 to 24,575 for the screen. And the last one, 24,576 is for the keyboard. So for the IO pointer. And we have a very special 4, which will occupy R0, our special 5 pointers, which will occupy R0. So this one is in R0, R1, R2, R3, and R4. This 5 is used later. We will not discuss it here, but just keep in mind from R0 to R4, this one is used for symbols for virtual machine. So this one is a virtual machine pointers. So R0 to R4 is used for VMs. And then after R4 is from R5 to R15 is used for the virtual registers. So this one is used for refer to the memory from 5 to 15 is also a predefined symbol. Okay, so This one actually is predetermined by the assembler. This is the predefined symbols. Now we can look at associated with predefined symbol. We can create a symbol table. Okay, so the symbol table looks like this. So the symbol table, the first one, I have R0 to R15. So from 0 to 15, assign a number. So if your assembler say R0 at R0, then I will assign the number 0 to it. And if you're in your assembly code say R15, then it will translate to 15. Hey, this is symbol is one-to-one mapping, right? Then the next one I will look at, this one is already right into the system is no matter you use it or not use it, your symbol table will include it. So screen will be starting at here and at keyboard, it will start at here. So this one is it will write like here in your symbol table. So this is the predefined. And this is also 5 predefined numbers used for virtual machine. Later we will discuss. Hey, all those things from here, from the beginning 0 to here is the predefined symbol. Now we look at the user-defined symbol. Okay, user-defined symbol. So after this line is the user-defined symbol. We have the first one is the right. Okay, how do I find the number for right? So this one will be line 1, line 0, line 1, line 2, line 3. If you have this control symbol here, it will not count the line. So HI will be line 4, line 5 for D equal to M. So I will continue 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Okay, right here is 18. So the first line after right is the line 18. That's why you will see that right will have the number 18. And so we continue 18, 19, 20, 21, 22, right? The first line after the and symbol is 22. So you will see that and will have 22. Okay, so this one is for the control symbol. Control symbol is quite easy. You just count which line after this symbol. And for this control, it will not give the line number. So this one will eliminate. But the first line number after this control symbol will be the number at here. So 18 and 22, 18 for right and 22 for and. Okay, so the last portion, I and the summation is the variables we use, right? Variables. So since the 0 to 15 is already occupied, so, excuse me. Okay, noise. So after that, the first available for the memory address is 16. So assembler will assign it when it look at, oh, this is the first symbol, the variable symbol is I, the second variable symbol is sum, then it will assign 16 to I and 17 to sum. Okay, so for the assembler. Okay, so this is, I generate the table. Hey, any questions? Okay, so far so good. Okay, so the last word for today's class is okay. When you look at this symbol table, all this one is automatically done by assembler. So, and used to translate the symbolic code into the binary code after you have the symbol table. And for the symbol table, so next class we will look at with the symbol table how assembler translate from your assembly language to the machine code. Okay, so that's all for today's class. Any questions?